So, hello everybody. Welcome back, at least some of you. Why do we look forward to the beginning of a new term? It's because there's going to be a new Ockham lecture in it. And indeed there's going to be. So, welcome especially everyone who joins us for the first time, the freshers and the graduate. And it's also a particular pleasure to welcome people who were once here and have gone out into the world. And of course couldn't stay there and came back to get a piece of this. Right, well, it's a great pleasure to introduce Professor Stuart Bale. Stuart's biography runs like this. He received his BA and PhD degrees from the University of Minnesota in 1989. Berlin Wall was just fallen, and 1994, respectively. He was a postdoc for 3 years at Queen Mary, University of London, during which my understanding is that he became an honorary Brit in spirit, and then took a research position at the Space Sciences Laboratory at Berkeley. In 2003, he was awarded the United States Presidential Early Career Award for Scientists and Engineers, and in 2004, Berkeley took the hint and appointed him professor of physics at the University of California, Berkeley. He was there as director of the Space Sciences Laboratory until last year. Stuart's interests are in fundamental plasma processes, such as turbulence, magnetic reconnection, shocks, and in questions such as what makes the solar wind blow, for example. The solar wind, as some of you may know, it represents one of the great failures of peer review system, and one of the great triumphs of intelligent conviction, which also became a great triumph of astrophysics theory. Eugene Parker discovered, as a young researcher at the University of Chicago, predicted the existence of solar wind theoretically. Referees roundly rejected his paper, and the great Chandrasekhar, who was then an authoritarian editor of Astrophysical Journal, overruled the referees and published the paper nevertheless, and then the solar wind was discovered observationally several years after. Thus, human intelligence triumphed. So, those were the heady days of space physics. But I have to tell you a somewhat dirty secret, familiarity breeds contempt. And so in the second half of the 20th century, as more and more spacecraft went up and into space and into the solar wind, a kind of attitude developed in astrophysics that the farther something is from the sun, the less well measured it is, and indeed the bigger it is, the sexier it is. So who cares about our little star and its surrounding puff of plasma when we can speculate about megaparsec-sized chunks of inscrutable dark matter bumping around in unmeasurable, vast intergalactic voids. Space physics became uncool, arguably, and increasingly focused on what Rutherford would have called stamp collecting. Stuart is one of the young Turks, probably the most prominent one, who in the first 2 decades of the 20th century made space physics great again, cool again. He did it, I think, they did it, I think, by training his focus on fundamental physics of heliospheric plasma, rather than on the zoology of observed minutiae. And not least, in the case of Stuart, by having a sharp talent for an iconic plot. So several of his most cited papers, if you look them up on the web, you'll find them, became famous by giving us an easy to read but profound in its implications image that distilled a key physical concept. These kinds of things have the power of setting the scientific agenda for vast communities, as you are about to see they have done. So Stuart, looked up on his website how he characterizes himself. And so he characterizes himself as an experimental plasma physicist. So his lab is space, and the helisphere, the solar corona, the solar wind, and the Earth magnetosphere. This is our own local patch of cosmic plasma. It's in many ways similar to the stuff that fills the voids out there between stars and indeed between galaxies, but there is a crucial difference. And the crucial difference is that we can stick probes into this stuff. They are spacecraft with instruments on them that measure electric and magnetic fields as well as distribution functions of plasma particles. And so one gets to do experimental plasma physics with such accuracy and across such ranges of physical conditions as are virtually never accessible even in the plasma laboratory on Earth, let alone accessible to observation in faraway cosmos. So that's the idea. As a researcher at Space Sciences Laboratory and as its director, Stuart has been involved in many such NASA missions. Today he will talk about arguably the most daring of them. So, ladies and gentlemen, I give you the 31st Ockham lecture. Professor Stuart Bale, who will take you to hell and back with a NASA spacecraft.
Thanks, Alex. Okay, so as Alex said, thanks. First of all, thanks for inviting me here. This is a terrific honor. So I'm going to tell you about the Parker Solar Probe spacecraft. So I'll give you a little bit of a run-up to it in terms of what motivates the science, a kind of history, a brief, reductionist, superficial history of the solar wind, and then I'll tell you about the Parker Solar Probe, and I'll show you some first results from the mission, and I'll ask you not to put any of it on social media. We have 4 papers under review in Nature, and about 70 papers under review in the Astrophysical Journal, and the Nature stuff is embargoed, so it shouldn't appear on Twitter before that. Okay, so this is a story about the solar corona. And so this is an eclipse image. If any of you have been lucky enough to see an eclipse with your own eyes, it's spectacular. You know, eclipses have been noted since, I mean, Plutarch had descriptions of eclipses in his journals. And one of the spectacular things that you see during an eclipse, so what we've done here, what's happened here, this is, I believe, a true solar eclipse. It's not an image from the spacecraft. So the moon covers the disk of the sun, the photosphere, and what you see above it is the solar corona. And what you see is that the solar corona is highly structured. Okay, it's not as homogeneous to the naked eye as the photosphere of the sun is itself. Okay, and we'll come back to this structure in a little bit. So this is a story about the solar corona. The story sort of starts, the modern version of the story, the far post-Plutarch version of the story, starts with with what's called the Carrington Event of 1859. So in 1859, in late August of 1859, Richard Carrington and Richard Hodgson were looking at the sun in white light, not with their naked eye. And what they observed was what we now call a white light flare. So they observed a brightening, a sharp brightening, and fairly rapid brightening on the disk of the sun, on the photosphere. That lasted, exactly, it must have been hours or so. And they reported it in the monthly notices of the Royal Astronomical Society. And then, oddly, a few days, well, before they reported it actually in the journals, a few days later, there was a kind of magnetic storm on Earth. So I think the observations were made on the 29th of August in 1859, and 3 or 4 days later, there was a disturbance of the magnetic field of the Earth that was noted by compass needles, changing directions over longer intervals of time, and telegraph systems went down. There were sparks seen coming from telegraph lines. The telegraph operators turned off their power supplies, and they were still able to communicate on the wires with no power in the system. There were telegraph operators who were shocked electrically shocked by the system. So there was a kind of magnetic storm. There were currents driven in the power grid, what was the power grid, the telegraph grid at the time, from changing magnetic fields in space. Okay, so eventually these two events were put together. Okay, it was considered that the Carrington event, this brightening on the sun, a few days earlier, was related to the change, this space-induced change in the magnetic field of Earth. But the puzzle of this is that the light travel time from the sun to the Earth is only minutes, right? It's not days. And so this was kind of the conundrum here, is that it was decided that they must be related somehow, but the transit time, whatever had left the sun during this white light event and come to the Earth to perturb the magnetic field of the Earth took days to arrive, not speed of light kind of times. Okay, so this was kind of the beginning of it, and it was posited then that there was that the space, actually the thought at the time was that the space between the sun and the Earth was mostly a vacuum. Okay, so there wouldn't be any medium to propagate information in apart from light. Okay, so this started to change that idea. The next part of the story comes when spectroscopists started to point their instruments through telescopes into the solar corona during eclipses and look at the spectroscopy of the gas, of the coronal gas from the ground. And there was initially some confusion about this. There was an idea that there was a new element. So there were, this is all sort of visible light stuff, right? 530 nanometers is green light. There was initially some confusion about this because these lines are not sort of thermal emission lines. These were measurements that were made through telescopes on the ground. And it turned out, it was a fellow named Bengt Edlund who understood that these were emission lines from heavier ions that were very hot. Okay, so they were immersed in millions of degrees of plasmas of millions of degrees. Whereas it was known that the photosphere of the sun, the black body spectrum of the white light star that you see in the sky, is more like 6,000 Kelvin or so. So you've got this cool star that's has a black body temperature of about 6,000 Kelvin, which actually, as far as stars go, is rather cool. And around it, you have this very hot, millions of degrees atmosphere, the corona. And it's a little bit of a conundrum as well, because in terms of thermodynamics, you think of the sun is presumably the source of energy for the corona, right? But usually you think of the heat as flowing from the hot object to the cold object, and not the other way around. So the thermal transport here is at this point is a little bit of a puzzle. So there were ideas here at the time of a static atmosphere by Sidney Chapman, and that atmosphere would be like the law of atmospheres, so the hydrostatic equilibrium at Earth. So you have gravity attracting the atmosphere down, you have thermal energy holding the atmosphere up, and so there's a scale height associated with that. But these ideas didn't work out. The scale heights are inconsistent with the scale heights that you see in the images of the corona. And it turned out that this idea was actually unstable, that if you construct a solar atmosphere using the law of atmospheres from hydrodynamics, it's an unstable system. Okay, so what comes next? So then the story is told, the way Gene Parker would tell the story, that the luminary that Alex noted, is that this fellow named Ludwig Biermann was visiting at the University of Chicago, and he went in to talk to John Simpson, who was kind of one of the superstars of cosmic ray physics at the time, who was the leader of the group at Chicago, to describe his idea about tails, gas tails, and dust tails around comets. So when comets orbit the sun, the tail structure behind the comet, as it comes closer to the sun, splits. Okay, and you see one tail. So here's a real picture of a comet close to the sun, and what you see is one tail always points radially away from the sun. As this comet orbits past the sun, one of the tails is always pointing away from the sun, and the other tail has some kind of arc-like structure. Okay, and Biermann's idea was that the arc-like structure, the tail with the arc-like structure, is dust, and it's being ablated from the comet. The comet is burning out, and it's being ablated, and it just enters into Keplerian orbit around the sun. Okay, so its orbit is determined by its initial condition as it leaves the comet. The other tail is what was called a gas tail, and it's actually probably more a plasma tail. And the idea of Biermann is that tail is picked up somehow and dragged away, radially away, that there's something blowing off the sun. Or that was kind of where he was going. That it has to do with the atmosphere of the sun. So he was describing this to, apparently the story goes, he was describing this to John Simpson, who was the superpower leader of the group at the University of Chicago. And Simpson said, you should go down the hall and talk to Gene Parker. He's just had a paper rejected from ABJ, which is from this Astrophysical Journal, which is related to this idea. So he went to talk to Gene Parker. That's a picture of Gene Parker when he was a young man. And Parker said, yes, this fits in exactly with my idea. So then Parker finally got his paper published in 1958. And the idea is that the medium between the sun and the planets is filled with a gas, and that gas is accelerated off of the surface of the sun and becomes a kind of wind, a supersonic wind that blows away from the sun. That gas, and he showed, and we'll look at this in a second, that he could construct a hydrodynamical system of equations that gave a solution like this. It explains the comet tails. It explains the Carrington event in the sense that there's a gas in the interplanetary medium that could carry a disturbance, a sound-like disturbance or a magnetic disturbance, rather than it being carried by light. So the basic idea of Parker's wind is that there's a gas that blows more or less radially, in fact in Parker's model, entirely radially away from the sun, and it carries in it a magnetic field. And we'll talk more about the magnetic field, the motivation for the magnetic field, but it carries a magnetic field and it just drags it away from the sun. Parker constructed a nice set of equations. Basically, it's just it's a hydrodynamic equation, a fluid equation. There's an equation of state. He includes gravity, and it's a steady state solution. In fact, it's structurally identical to Bondi accretion, if you know about accretion. And so this is a plot from Parker's paper of the wind speed, the speed of this gas blowing off the star, normalized to the sound speed. Okay, so where this is 1, that's Mach 1. That's a Mach 1 flow. And above that, it's faster than the speed of sound. And the axis on the bottom is basically the radius, the distance from the sun, from the surface of the sun, normalized to some critical radius, which we don't need to concern ourselves with. So 1 is the critical radius. So this is the point, basically, where the flow goes through the speed of sound and becomes supersonic. So in some sense, in the sense of a simple fluid like this, it's the point at which the gas can no longer transmit information back to the star. So after it's left that point, it's a wind. Okay, inside of that point, it's maybe a corona. So it's more complicated in the real world because there's a magnetic field, so there's more critical points, etc. But it's also we'll come back to this. Okay. So this is Parker's model, very simple. But the key thing here is that it requires more energy input than you see just with the thermal pressure of the solar wind. So there's thermal pressure, there's an equation of state, there's gravity, and then there's dynamics. So there's a heating problem. So the solar wind, the model seems nice. It gives you asymptotic values actually that are consistent, as Alex pointed out a few years later. This was published in 1958 and 1962, I think. The Mariner spacecraft, and there was actually a Russian spacecraft around the same time that flew out beyond the Earth's magnetic field into the interplanetary medium and directly measured the solar wind. So the theory gave a prediction that was confirmed, which is not all that common. And the energies, the velocity, the flow velocity of the wind that was measured is consistent with the Parker model. But it requires some source of energy input at the base. Okay, so that's, I had this too. So these are modern measurements of, so this is again, this is the distance from the sun normalized to the radius of the sun. And this is the velocity, now in crude kilometers per second units. The white circles, the open white circles here, are measurements that have been made with instruments that occult the disk of the sun, so they create an eclipse in their field of view on the camera, and they take pictures as a function of time, and you can see structure. This is white light structure, so it's basically it's white light, it's Thomson scattered white light. So light that leaves the sun scatters off of plasma and comes back in the direction of the Earth, and so it's telling you about the plasma, the density of plasma in the sky. And you can measure little blobs in these camera images and watch them propagate out. And you can measure their speed as a function of radius, and you can see that they actually are accelerated out in the manner that Parker would suggest. And it's also the case, this is a little bit more complicated. The green dots here are basically Doppler shift measurements, speed that's inferred from the Doppler shift of spectral lines of heavier ions. And they give a similar kind of result. So there's evidence from remote sensing measurements of the acceleration of a wind away from the sun, and we know that that wind exists at 1 AU. So we're convinced that there's a solar wind, and we're convinced that there's a solar wind acceleration region. We're convinced that there's a region close to the sun where the wind is still forming, is still being accelerated out, heated somehow, and then energized to go through this critical point and become a freely propagating wind instead of a corona. We also know that the solar wind the speed of the solar wind is bimodal. Okay? So these are graphics from using data from a spacecraft called Ulysses. Ulysses was a European Space Agency project that flew over the poles of the sun. So it went out to Jupiter and got a gravity-assisted Jupiter to sling out of the ecliptic, and it went mostly normal to the ecliptic over the poles of the sun. And these plots, so this left-hand plot is during solar minimum. It's when the solar cycle is at its minimum, when the sunspot number is very low. So solar activity is most modest at this time. So this is sunspot number on the bottom. Okay? And what you see when you go over the pole, so the radius of this data that's plotted on here is the speed of the wind. So we see that there's wind that's faster over the poles, North Pole and South Pole, than in the equatorial plane, the ecliptic plane of the planets. In the equatorial plane, the wind is more sporadic and structured, and it's slower. So what we see at 1 AU typically is this kind of bimodal nature. There's fast wind, what we call fast wind, which is 500 to 1,000 kilometers per second, and there's slow wind, which is half that in speed. The slow wind is denser, and it's more turbulent. It's more mixed up. The fast wind is rarefied and highly structured, more structured, and we know that it comes primarily from over the poles. The second orbit of Ulysses was during solar maximum, and now you see all this structure imposed on top of it. Okay, so when there's a lot of structure, when there's a lot of coronal structure near the sun, on the sun, in the corona, the wind speed is more intermittent. Cycles between fast and slow wind. Okay, so the kind of paradigm that's emerged from this is that there are two kinds of wind, fast wind and slow wind. The fast wind emerges from polar coronal holes, primarily, or their extensions down into the equatorial plane. The slow wind, it's not clear. What is the source of the slow wind? At least this is the existing paradigm, is that the slow wind could emerge from coronal holes, but there are very few of them near the equator. It could, we'll talk about that in a second. It could be the result of fast wind from the poles overtaking itself and creating a kind of instability where imagine two streams intersecting each other and mixing, and so that slows down the whole thing. It becomes more turbulent, more mixed, more dense. So there's a kind of family of ideas as to where the slow wind comes from. And I think this is one of the problems that we've solved already with the first few orbits of the Solar Probe project. But it is one of the outstanding puzzles. Okay, and then back to this. So here's the picture I showed again, and of course this is just, if you just drop, I took this off of Wikipedia, this is a dipole magnetic field, you just drop it on top of this thing, and you see that it's pretty suggestive, right? So the solar corona is magnetized, and this turns out to be very, very important. But we think the magnetic field is what does all the I won't say work, but it is what does the work here, and makes the contact between the photosphere and the corona. The image on the left is a soft X-ray image of the sun from, I believe this is from the TRACE spacecraft, a Japanese spacecraft. And what you see, if you look at this in soft X-ray, so you're looking at plasma that's millions of degrees. As you see, and this is during, these are all sort of sunspot areas here. What you see is loop structure. I mean, it's maybe not trivial to see it here, but the magnetic fields that emerge from below the photosphere out into the corona are often loops, like envisioned here. So there's some dynamo process in the outer sort of 1/3 of the radius of the sun. The sun it's a hot fluid, and it's boiling, and you have convection. and you have convection cells. But the fluid is partially ionized, so it has charge. And so you have currents, you have kind of cells of current, and those cells of current generate magnetic fields. The magnetic fields loop up. Some of them are closed, often they're closed, but some of them are open. And the field lines that are open can carry plasma out. Okay, so these open field lines should be the source of the solar wind. They're the field lines that extend out into interplanetary space and carry the wind with it. But below that, or adjacent to that, there are loops, closed loops of plasma that may have hot plasma on them, but they're not open. It's not escaping plasma. So that's kind of what this is meant to show. You can see loop-like structure in here. You can also see open structure, which is consistent with this cartoon. Okay, so the models that we have for heating the corona have basically fallen into these two kind of cartoon representations. One is that the magnetic field that emerges from the photosphere is the open magnetic field that emerges from the photosphere is wiggled around. The foot points of it are stuck in these convection cells below this in the photosphere, and as those convection cells wiggle around, they shape the magnetic field and they generate waves, and those waves carry energy out into the corona, and then somehow that energy heats the gas. So the magnetic field is the intermediary between the mechanical motion associated with convection and the corona, the heat of the corona. So it's basically the magnetic field is taking kinetic energy from convection, turning it into heat in the corona. This is one scenario. The other scenario is a scenario called magnetic reconnection. In magnetic reconnection, you have an interaction between open fields, so this is a funnel of open field lines, and closed loops. Okay, so if at this point with the green action going on there, if the magnetic field of the loop, say, is inward, and the magnetic field of the open line is outward, so they're opposite polarity, then they can annihilate one another. So where they meet, you have essentially zero magnetic field if they're equal and opposite. But that energy density associated with the field has to go somewhere, and so in this model of reconnection, it goes into the plasma and accelerates the plasma outward. So we've got a scenario where we've got these kind of these two classes of models for how the magnetic field heats the solar wind, the corona, which becomes the solar wind. There are other models involving antipolar electric fields and collision with shock waves and other things, but this is kind of where the community is focused at the moment. Okay, and so then the big idea here is basically that whatever happens down here injects energy, the magnetic field carries that energy out into the corona, and then some process converts that magnetic field energy, mechanical energy in the magnetic field, into thermal energy in the gas. And that thermal energy in the gas then allows it to escape the gravitational well of the sun and become a wind. So most of these models, again, involve turbulence, some kind of process of turbulence where we initiate a cascade in turbulence, and the cascade takes us to scales where we can heat the plasma. This is a nice cartoon by Ben Chandler. So that's kind of the state of the art, is that we understand that there are magnetic fields. The corona is hot, millions of degrees. It's magnetized. The magnetic field is generated by currents due to convection in the photosphere, in what's called the convection zone. And that magnetic field is carrying the energy of that convection out into the corona. That energy is somehow heating the plasma. Okay, so that's kind of where we stop. Okay, so long before we had this sophisticated of an idea, but after we already knew that there was a solar corona and a solar wind, there was a report in the US issued by the National Academy of Sciences and the National Research Council, led by John Simpson, the guy who sent Ludwig Biermann down the hallway to talk to Gene Parker. And this report, which is called the Simpson Report in the lore, set out an agenda for 3 major spacecraft projects that NASA, which had just been started, actually NASA was founded in 1959, I think, that NASA should initiate. And the first one at the top of it was a solar probe. So, specially designed payload capable of withstanding high temperatures to be aimed close to the sun. It was the top priority in 1960 of NASA. The second was a probe called the Interstellar Probe, The idea was to go out of the solar system, to go into the interplanetary or the interstellar medium. And I was talking to some of the students just beforehand. We're now studying this very seriously. I've just been in Manhattan and New York last week for a workshop where we're actually putting together a mission design to try to do a deep interstellar medium mission. And the third was a spacecraft to go over the poles of the sun and understand from above what the solar would look like. And that became Ulysses, which was launched in 1990, I believe, by the European Space Agency. So this one is done, dead and gone. This one we'll talk about next has just been launched. And this one we're trying to get into the process to be launched. We're trying to get it up in 2030. It would have a 10-year trip to the edge of the heliosphere and then exist for another 20 or so years afterwards. So this would be a project that went on till 2060 or so. Okay, so Solar Probe. Solar Probe started in the US. Actually, there was a concept called Vulcan, a Russian concept that dates from kind of the time of the Simpson report too. And I've never been able to, the only person who I know who knows a little bit about this is Ian Roxburgh. I don't know if you all know Ian Roxburgh. He has some reports on Vulcan that he could talk about, but I don't know much about it. But after the Simpson report, there were several studies in the US to try to design a solar probe mission. And these are just some concept ideas. On all of them, what you see is a big heat shield at the top. So the sun is infinitely far in that direction, and all these pointy hat things are pointing at the sun to shield the spacecraft behind it from the sun. The major engineering challenge of a solar probe mission is just the radiant heat from the sun at low altitudes as you get close to the sun. So there were mission concepts. I guess this one is from, what does that say? Is that 1990, 82, I don't know, 99, 92, 93, 94, 94, 94, 94, 95, 95. This mission concept actually led to a NASA announcement of opportunity. They put it into their plans. They coupled it with a mission to Europa and a mission to Pluto. And they took proposals, and people wrote proposals. My group worked very hard on the proposal in 2000, 2001. And then they decided they couldn't afford it. And so after they made the community work hard on proposals, they didn't select anyone. And they went back to the drawing board and commissioned a new study on a mission that wouldn't cost $4 billion. Okay, this concept had a price tag of about $4 billion US. And they wanted a mission concept that would cost more like $1 billion. So they commissioned a new design, and that ended up being Solar Probe. We launched last year.
2, 1, 0.
On a Delta IV Heavy spacecraft, which is
Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on
a little
the
propaganda
mysteries of
here.
our closest star, the Sun.
NASA likes that. So we launched on a Delta IV Heavy, which is kind of the biggest rocket that NASA uses for scientific payloads. It has a central core and then two what are called strap-ons on the side. The system had 3 stages. We had a failed attempt on August 11th of 2018, last year. The first night it was aborted, and the second night we went at about 3:30 in the morning. I don't know if any of you have had a chance to, but if you do have a chance, it's spectacular to go see the launch at Cape Canaveral. It's really, especially a nighttime launch like this, it's really, really cool. The power of the thing is just astonishing. When that shock hits you, the sky lights up first. I have another movie that I guess I don't have in here that I took with my iPhone. The sky lights up as they burn off all the gases off the rocket, and then when it goes up, it gets up above the cloud layers before the sound wave, the shock wave hits you associated with the sound. And it's just so non-linear. The audio is, the sound is so non-linear, it's just stunning. It's not like anything you have experience with. So we launched on a Delta IV Heavy on August 12th of 2019. We went to Venus. I'll show you actually I have it on the next slide here. This is the mission design. So this is a little movie showing us coming off with a green object coming off of Earth. But at the top thing here, you can sort of see really what the action is. We went first to Venus on October 3rd of last year, and we had a Venus gravity assist. So we burned some hydrazine thrusters in your Venus to slow the spacecraft down, reduce its angular momentum so it'll fall into the sun. The problem is that when you come off of the Earth, you have the angular momentum of Earth, and that would keep you in orbit around the sun at the Earth's radius. You want to slow the spacecraft down. So in the tangential direction. And so we did that, and then we've had 3 orbits since then at a perihelion altitude of, so the red curve here is the red curve is the spacecraft distance from the sun. So after that burn at Venus, the aphelion distance stays sort of near Venus, and the perihelion altitude came down to 35 solar radii. And so we've done 3 orbits like that. And then later this year, actually on Christmas Day, I think, or maybe the day after Christmas Day, Boxing Day, you say, we have another Venus gravity assist. And so we'll pass by Venus again, and we'll burn the hydrazine thrusters and slow the spacecraft down and drop down closer to the sun. So starting in January, we'll have perihelia at about 28 solar radii. And then we have 5 more. So in total, we have 7 Venus gravity assists, Venus encounters. And at each one, we slow the spacecraft down. And then in the time frame of 2024, 25, we'll get down to about 9.86 solar radii. So this is from the center of the sun, so 8.86 from the surface of the sun, from the photosphere. And that's our final distance, and that is the distance at which we think we should be well inside of this critical point, the point where there's a discontinuity, where the wind becomes actually what we call super-alphanic. It's faster than the speed of magnetic field perturbations in the plasma. In some sense, theoretically anyway, it's the point of the discontinuity in the angular momentum. So inside of that point, the corona can be considered as to be rotating rigidly with the sun. So the magnetic field and the plasma are rotating rigidly with the sun. Beyond that point, it's an escaping wind. Okay, it's probably not really discontinuity in the angular momentum, but if you write out a simple energy equation, it is. Okay, so that's the goal, is to get down to 9.86 solar radii. And when we get down to that altitude, this panel, where is it here? I misspoke here. The red is speed, so this is the distance. The red is speed. When we get down to those altitudes, the spacecraft, the Keplerian speed of the spacecraft when it's at its closest point to the sun will be about 200 kilometers per second. Okay, so that'll be the fastest ever man-made object at that point. It's really flying through the corona. That's a picture of the spacecraft. I'll show you more in a second here. So there are 4 experiments on the spacecraft. One of them is called Fields. This is the one that I lead from Berkeley. And what we do is we measure the magnetic field. So we have what's called a search coil magnetometer at the end of a boom behind the spacecraft. We have some flux gate magnetometers, and then we have these electric antennas that deploy out into the plane of the heat shield. So this is probably a good time to tell you a little bit about the spacecraft that we built. I don't know if you can see this very well, but there is a heat shield at the front. So the spacecraft itself is back here. This is a heat shield, and the heat shield is about, it's I think 2.7 meters in diameter. It's mostly circular, and it's built of a kind of carbon, vitreous, what's called carbon-carbon. It's basically a carbon, kind of an array, a mesh of carbon that's impregnated with vitreous carbon, and it makes a kind of a lightweight, high-temperature cup. Okay, and then inside of this cup is a kind of aerogel, a kind of foam, a carbon foam, and on the top surface is a ceramic faceplate, a material that's called alumina, which is a high-temperature ceramic. So that alumina faceplate points to the sun. Behind it is this carbon structure. The edge between that ceramic, I'm telling you this for a reason, the edge between that ceramic faceplate, there's a few inches of space between the ceramic faceplate and the edge of the cup, and that's closed out with a kind of felt that's made of carbon as well. Okay, so it's something that was stitched on, glued on, all the way around the spacecraft. Okay, behind that are a set of radiators. I don't know how well, I guess you can't see that. We're looking through the structure here. The radiators are on the top and the back, and we pump water through those radiators. Okay, and we take water off, we take heat off the back of the heat shield and run it through those radiators. Everything behind this heat shield sees only the black of space, right? So it's just pure radiative heat transport. The reason we use water is because it's non-corrosive. And so you can actually let it stay in space for a long time, and it has a very high specific heat. It's good at carrying thermal energy away. And incidentally, for launch of the spacecraft, this system is so efficient. So the front surface of this thing will be at about 2200 C at the close perihelion. It's going to get very hot. The antennas that my group built, which deploy out into sunlight, will be 13 or 1400 C. They'll be glowing at perihelion, at the close perihelia. But behind here, this front surface of the spacecraft, which is, which has these radiators between, is only rated to about 40 or 50 C. We tested to, I think, 55 or 60 C. Okay, so the efficiency in taking heat, there's a megawatt of energy on this front heat shield at perihelion, and the spacecraft itself operates at more or less room temperature, like a hot day in Athens or something. So it's a very efficient system. Behind that is the spacecraft. The spacecraft itself is about, I could maybe almost put my arms around it, and it's about my height or so. It's a big kind of canister. It has panels that open up on the side of it, and it's full of, actually it's an astonishing work of art. The wiring loom that they had, that was built to wire everything together in the spacecraft, had to be built in a way. The group that built the spacecraft, which is at the Applied Physics Lab at Johns Hopkins, which is a kind of quasi-defense, quasi-civilian space organization, they built a mock-up of the spacecraft, okay, a true-to-scale mock-up, and they put all mock-ups of all the boxes that had electrical connectors in them on them, and they put the right electrical connectors on everything. So this took months to build up this replica of the spacecraft. And then they wired up a wire harness to the replica and tested all the continuity of all the wires, all the mapping of the connectors, etc. And then they disconnected all the connectors and lifted it out with a crane and brought it across the clean room and dropped it down into the real spacecraft. And it's just thousands and thousands of wires with connectors on. Dropped that down into the spacecraft and crawled inside and connected all the wires. Just an astonishing feat of engineering. There are solar panels behind here. I guess you can see the solar panels here. And the solar panels, so we don't have an RTG, we have an actual electrical system. The solar panels flip out into sunlight when we're far from the sun, and they charge the batteries. And then when we get close to the sun, they tip back. It's a closed loop system that happens automatically. And when we're close to the sun, only these little illuminated tips hang out into sunlight, and they keep the battery charged as we go through the perihelion. And these little tips of the solar panels have active cooling. They have water pipes on the back of them as well. So that's basically the architecture of the spacecraft. I'll talk a little bit, there are 3 more instrument suites. There's an instrument suite called SWEEP, solar wind electrons, alphas, and protons. This measures the thermal plasma, so there are detectors back and behind the heat shield, in the shadow behind the heat shield that measure these. This is led by Justin Casper of Michigan. These sensors were built in my lab at Berkeley as well. There's an instrument suite called ESIS. It was originally called ISIS, but then that name was co-opted by another group. So the name was changed to ESIS, and this is an instrument that measures energetic particles. So from, say, 20 or 30 kilovolts up to several megavolts of energy, ions and electrons, and that's a set of detectors that sit behind the spacecraft as well in the shadow. And then finally, there's an instrument called WISPR, the Wide Field Imager for Solar Probe. And WISPR is a white light imager, so it's a kind of camera with a set of baffles. It looks out over the edge of the heat shield, so it can see only down to a couple solar radii. They don't want to look at the sun; they would be saturated by the sun, so they look down to a couple solar radii, and then out to where the scattering cross-section, the Thomson scattering cross-section, falls off. So maybe 100, 120, 130 degrees away from the sun, and up and out of the ecliptic. So they're basically imaging in white light. So this is plasma density, essentially. They're imaging the stuff that the spacecraft is flying into. So they see it before we hit it with their camera. And this is what this is another propaganda video. So this is I'm going to show you data from our first perihelion pass, which was on November 6th of last year. It was almost a year ago, at 35 solar radii. This data is we still haven't released this to the public, incredibly. We have a requirement to release data 6 months after it's all on the ground, and so that 6-month time will come up on November 12th of this year. So in less than a month, all of the first encounter data will go public, and you're all welcome to look at it, to dig into it. So what Whisper saw on this first pass was basically the wind emerging. This is their imager. So that's actually Mercury. So they've done some image processing to blot it out, so it looks bigger than it really is. And this structure is a magnetic flux rope emerging from the sun. So the sun is down here, obviously, and this is interplanetary space. And so they're seeing the streamer structure of the solar wind up close. And there's work going on right now to look at turbulence spectra of this, to follow structures out and try to infer wind speeds. That big loopy structure that you see here is called a coronal mass ejection. We've seen a few of those. We've flown through them and measured their plasma. And an interesting thing here is if you look at all these streaks that you see in the images, these are dust impacts. So one of the things that we knew we would encounter, but we were encountering at a surprisingly high rate, potentially a dangerous rate, are dust impacts on the spacecraft. My instrument measures voltages, spacecraft voltages, and I can see the spacecraft voltage fluctuating whenever a dust particle hits it. The white light imager people measure these streaks of stuff, and if they do ray tracing of the streaks in their camera, they find that they all come from the edge of the heat shield, of that thermal heat shield on the front of the spacecraft. And in particular, we know, and the transit time, they look fast here, but they can measure the speed. They take several images and they can measure the speed of these tracks across the image. The speed of these tracks is only, say, 20 centimeters per second, so it's not super fast. Okay, so they're moving, at kind of a finite speed. So what we think this is felt from that little strip. This is what I mentioned. There's a little strip of felt around the edge of the heat shield, and we tested like crazy. We knew that if you shake this felt, pieces of it come off. And we were worried about this for the launch environment. The launch environment is terrible. We were worried that bits of this carbon felt would fall off and gum up our instruments, that sort of thing. So we convinced ourselves that wouldn't happen. But we hadn't anticipated that every dust particle that hits that thing would kick off little fibers, and those fibers would drift away. You see them in the camera. So we're a little concerned about this. This is actually the highest risk right now in the spacecraft, is the dust environment. There's an independent study going on to try to decide. We're going to introduce a process where we decide for each Venus gravity assist that we're going to actually lower the altitude of the spacecraft, that we can accept the risk associated with all the dust particles. If the dust particle, a big enough dust particle, hits and ruptures a water line on the spacecraft, we could lose our coolant and be finished. Okay, so that's what the white light people see. Now I'll show you data from my instrument. So this maybe won't appear as spectacular to you because you're not all solar wind physicists, but this is the magnetic field. This is the radial magnetic field pointed away from the sun through the solar comet. So we started out here. This is the distance from the sun, 100 solar radii, down to at the center of the red thing there is Perihelia, 35 solar radii, and back out. The envelope that you see on top of here that has a red dotted line on it is 1 over r squared from the distance from the sun, which was crudely the expectation for the magnetic field. We thought we would see a magnetic field that scaled like 1 over r squared as we went into the sun and back out. And we do see that the envelope of it looks like 1 over r squared. But on top of the envelope, you see all the structure. The structure has a change of delta V over B of order 1. So the magnetic field is flipping around in direction order 1 on time scales. In fact, there's no time scale associated with this. This is you can see this is a month of data, and it comes down to time scales of a fraction of a second. There are reversals of the field on time scales of a fraction of a second. The bottom panel is that same data where we've attempted to remove those fluctuations. So what we've done is run a filter across it and compute histograms and find the peak of the histogram. It's a mode, basically a statistical mode. So this is more like what you would expect if you had a steady state, a simple steady state solar wind. And what we see is, 1 over r squared behavior, and we see polarity reversals. So we see regions where so this is, here blue is inward, the magnetic field of the sun is pointed in, and then we come into regions where the magnetic field flips sign and points outward, inward and outward. So what's happening here is we're crossing a current sheet. So we're crossing regions of connected magnetic field below us. So the magnetic field is being dragged out by the solar wind, and from a region with one kind of polarity into a region with another polarity. So we're crossing structures below us on the surface of the sun. If you take that magnetic field profile, the color of it, the inward or outward polarity, so here again, blue is inward polarity, magnetic field pointing into the sun, red is pointing outward, and drop that on the orbit of the spacecraft. This is the orbit of solar probe. It came in, like this is in a system called Carrington coordinates. So basically the sun is at rest below us, okay, in this system. So the sun is rotating, obviously it is a 27-day period. The spacecraft is moving, okay. The spacecraft became, any point on the sun below us is moving faster than us until we get to a point of what's called co-rotation. We're rotating with the sun. Then we became prograde. We went to a lower altitude, became prograde, came back out, and became retrograde again. And so what you see is a kind of loop in like this. We came in, we looped around, and then went back out. The color of these magnetic field lines, these are model magnetic field lines, colored for their polarity. If you take that color and drag it all the way out to 1 AU, this is the orbit of Earth out here, and then use a measurement at 1 AU from a spacecraft at 1 AU, you see that that color mostly agrees. Okay, so basically the magnetic field that you see near Earth, in the solar wind near Earth, the polarity of it, the sign of it, inward or outward, can be traced all the way back into the spacecraft of solar probe, the altitude of solar probe. It basically preserves that structure from the solar probe altitude all the way out to 1 AU. This is work being done by a student in my group, Sam Badman, who did his first degree here actually at Keble College in Oxford, and now he's doing a PhD with us at Berkeley. So what we do to model this, we apply a really simple model to understand this, and it's turned out to work really well. And that model is what's called a potential field source surface model. So basically we assume that the magnetic field of the solar wind is current-free, so there are no currents. Okay, so we can say the curl of B is equal to 0. And it's steady state, so it doesn't evolve with time. And we take an inner boundary condition, which is basically at the photosphere. So if you do that, you have a potential model. You can solve a Laplace equation for a potential. And we need a boundary condition at the photosphere and a boundary condition at some other altitude, which we call a source surface. So the photospheric boundary is given by measurements of the magnetic field, the line of sight magnetic field made from a spacecraft or from a telescope on Earth using Zeeman splitting. The magnetic field splits the line emissions in let's say UV or even optical, and then you can by measuring the splitting you can infer the magnetic field at the source. And so we can have a measurement of the magnetic field at the photosphere. It's called a magnetogram. And then at the source surface, we assume that the field is entirely radial. Okay, so the divergence of B is 0 there, and that's the point at which the wind escapes. Okay, so below that height, you can have loops, you can have closed loops. Okay, but at that height and above, everything is open. Okay, and so this turns out to be enough to solve for the magnetic field from this surface downward to give a model of the magnetic field below, in other words, you can take a magnetogram and predict the magnetic field, or measure the magnetic field here, and propagate it out with the boundary condition here. And then beyond this point, everything is escaping. It's all wind. So you can just infer that it's blowing out away and compare it with your data. So my student Sam has done this. This is a model. This is his run. So he's taken magnetogram data. The polarity that you see, the red and blue there, are the polarity during the solar probe encounter. And then he's applied this source surface model, and these field lines are the magnetic field lines that are consistent with that. Here I think his source surface height is 2 solar radii. So this height, the height at which you take the wind to be escaping, is a parameter in the model. If you make it lower, you clip off more magnetic field. You clip off the tops of loops, you open more magnetic flux, you have more structure. If you take it higher, you can take it out as high as you want, but you want to generally find the lowest point possible. Conceptually, what it corresponds to is it's the point where the wind escapes. So it's the point where the thermal, or the energy in the plasma, in other words, the thermal energy and the kinetic energy density of the plasma, is comparable to the forces that hold it down. In other words, the magnetic field energy density and gravity. So it's kind of the point where, so the magnetic field of closed loops and gravity are confining the plasma, and the plasma thermal and kinetic energy are pushing it out. So it's kind of the balance of those points. Okay, so Sam has done that, and if you then take the surface height as a parameter, you can predict what you would see at solar probe. And these colored bars correspond to different heights. So these are different heights at which the wind escapes. And so this plot is kind of messy, I apologize. But what you see is that some of these polarity features, this red stuff up here, the dots are the data, can only be predicted by putting the source, the black or red, the source surface low, 1.3, 1.5 solar radii. Whereas some of the features correspond to almost any source surface height. You can get all this structure with any height of escape. And out here, if you look at the dots here, at this point, you need the higher 2.5 or 2.0 source surfaces to keep this red polarity out here. If you take the low source surface, it clips off too soon. So what this corresponds to, this is a map now of the magnetic field at the source surface, at the height of escape. And this is the trajectory of the spacecraft plotted on top of it. So where it's red, you have outward magnetic field. Where it's blue, you have inward magnetic field. What we see is that we can map this nicely. So here we have blue magnetic field, which is consistent with this. We cross this line, which is a current sheet. It's a polarity inversion. That's where the field, the line, the polarity of the magnetic field changes. So there's a current there. Then we have red, blue, red, etc. So we can basically measure the height. We can find a height that's consistent with this simple model from which the solar wind is escaping. And what we find out, this is a nice plot too. This shows the same thing in radius. So this is the distance from the sun. This is the longitude. So the spacecraft comes in. This is the trajectory of the spacecraft. It comes in here, dips down at Perihelia and goes back out. Now the color of the magnetic field is the measured polarity at the spacecraft. This line shows the source surface height. So basically what you can see here conceptually is that if you take the source surface to be too high, you don't, see this is blue, you don't clip off any of that red magnetic field. You don't clip that loop off. You need to clip that loop off to measure to be consistent with the spacecraft. You need to clip this loop off to bring positive polarity magnetic field out to the spacecraft. So if you drop this source surface down, you can do it. If not, you can't. On the contrary, in this case, you have to have the source surface be high to let the solar wind expand out and fill this volume. If you take it too low over here, you're clipping it out too low, and you don't predict the right polarity either. The source surface is actually not a surface; it's not a sphere, okay, which is not a surprise. Okay, why would it be? But we can now measure it, so we can measure the structure of the region from which the wind actually becomes a wind. It leaves the corona and starts to escape as a wind, and it's not spherical. It's we optimize this model as we fly through Perihelia and find a source surface which is highly structured. This is the work that Olga Pansenko is doing. And finally, all these structures that we see, these things we call them jets or switchbacks. These changes in the magnetic field very rapidly, we think are maybe related to the solar wind heating problem. This shows you the spacecraft, the longitude of the spacecraft. So we have, this is co-rotation, this is co-rotation. So in this region here, the spacecraft is hovering over the sun. It's rotating with the sun. So there's no relative motion between the spacecraft and the sun. This is the longitude of the foot point of the magnetic field back down to the sun. So we're maybe 10 degrees off or so. And so if you look in here, we're basically hanging over a point in the sun, over the sun, and we see all this magnetic structure flipping around, flying past the spacecraft. Okay. On this time scale, this is 2 weeks of data. This is minutes of data. So there's a reversal right there in the magnetic field. This structure is carrying pointing flux. So these are again these jets, what we call jets. These flipping around in the magnetic field. There are associated increases in the velocity. These little blips here are the velocity being carried. So there's an enhancement in velocity, and there are enhancements in pointing flux. This panel here shows the pointing flux, the electromagnetic pointing flux. So we think this business, these large field reversals, 180-degree field reversals, magnetic field on all these variety of time scales carry pointing flux out into the corona. We think this is maybe part of the role of what heats the solar wind. Doesn't look like a wave. It's alphanic. For those who know about alphane waves, it's alphanic mostly. These structures are, but they don't look like. It's hard to imagine taking the foot point of a magnetic field and wiggling it around and having it flip polarity entirely. So I'm starting to favor the reconnection models. It's also the case that there are observed, this is a UV image of the sun, a movie of structure on the sun, and okay, it's maybe hard to see in here, but there are things that we call jets or spicules in the remote sensing measurements. There are little blobs of structure that move out away from the sun quickly on timescales that are comparable to these timescales. So I wouldn't say yet that there's a one-to-one correspondence, but I think it's likely that there are remote sensing measurements that correspond to these little jets of plasma that we're seeing. So this is our second early result. I think our first early result was that that this question of does the wind, maybe I'll go back to Sam's other plot here. Does the wind emerge from, the slow wind emerge from the coronal holes, the interaction of polar coronal holes, or from the equatorial plane? We've answered that. We can see solar wind emerging from, this is our perihelion pass. This is a small coronal hole, the dark part of it is cooler plasma. This is a UV image of, sort of 1,000,000-degree plasma with the spacecraft trajectory plotted on top of it. All of that blue magnetic field there maps right back down into that little teeny coronal hole. So the plasma is emerging from that coronal hole and it's expanding out to fill space. There are loops around it, but it's expanding out to fill space. So we think that it is possible for small equatorial coronal holes to generate space-filling solar wind. That's one of our first big results. And our second result, I think, is that we are now seeing magnetic structure with the right time scales and with some still kind of mysterious geometry that injects Planck flux into the plasma and may be responsible for heating the wind. Okay, so my summary is that it's a gold mine. The first three perihelia are terrific. I mean, there's a bunch of stuff here that I couldn't even touch on. The wind itself is highly unstable. If you know about plasma physics, the velocity distribution functions are full of instabilities. There are waves that are being generated locally. It's very, very exciting. It's not at all like the solar wind that you see near Earth, which is a turbulent, more or less fully evolved turbulent fluid, magnetized fluid with some intermittent, exciting stuff in it. It's structured, it's unstable, it's very different. And we're just getting started. So we've just had the first three perihelia passes. As I said, in January of next year, we start to have perihelia at 28 solar radii and down and down. So it's one of these really cool missions where, NASA likes you to declare mission success within 2 years when they launch a mission. They want to declare mission success in 2 years so they can start to ramp down your funding, basically. And this is one of those missions that it gets better and better. It'll be 2024 before we really start to have the most exciting data, I think. And if things continue to function on the spacecraft, I'm optimistic that they'll operate us for years after that as well. So that's my story. So we're just getting started. I think we'll have a kind of press splash probably yet this year in November, early December, where we release the first results and there'll be some papers and some NASA luminaries talking about their accomplishments. That's it.
Thank you, Stuart, for this exciting trip to hell and back, as you said. It appears to be a paradise.
And back.
And back. But it appears to be paradise rather than.
Yes.
It's also very useful information that the data is getting released on the 12th of November.
It is.
And so, you've heard it here first. You can find out at dinner how to download it, and so this is your quickest route to world-shaking discoveries. So
we hope you don't scoop us.
But let me now call for questions and see who wants to ask what. Please.
How big of a risk would you say is the carbon lining between the two plates failing until 2024? You said after 2024 we're supposed to get the most exciting results.
Yeah, so this is a good question. So we actually only kicked off, the spacecraft team has kicked off a study of this. So there are models of the dust environment of the inner history, and those models were taken into account. They did Monte Carlo simulations, etc. But we're seeing more dust than the models predicted. So now there's an attempt to try to correlate, to rekit the models with the new data and try to do some studies of probabilities of failure. It's also the case that that there is a predicted dust-free zone deeper in the heliosphere, and the WHISPER instrument. So those images I showed you of the the dust impacts and the whatever, that's what's called the K corona. The structure that you're seeing in the plasma is what's called the K corona. The F corona is light from dust, the zodiacal light, it's called, and that was removed from those images. That dominates their data, and they think they can start to see the kind of fall off of dust in the inner heliosphere, okay, as they're looking closer to the sun. And so if that bears out, that will help the case. Okay, we may actually have the spacecraft down to an altitude where there's less dust. We're probably flying through a kind of, or we're going to encounter a local maximum in the dust rates. But we don't know. I mean, there's a effort to simulate this and to do some fault analysis and to see what the probability is. It would be a mess. It would be terrible if we lost it.
Yeah. Okay, thank you.
What's going to happen to the spacecraft after the mission's done?
Well, it's a good question. I mean, it's not designed to go lower than 9.8 solar radii. Okay, so what would happen, I mean, in principle, we could probably steer it past Venus again and do another Venus gravity assist, but eventually the umbra closes and the umbra becomes too small behind the spacecraft. And there are star sensors and what are called limb sensors, and there are all kinds of things that keep the spacecraft pointed that require that can be put into sunlight. So we won't take it lower than that, unless someone gets really daring and they just want to do one last plunge. What will happen probably is that either something will fail on the spacecraft. If enough instruments fail, eventually everything will fail. But as instruments start to fail, NASA will make decisions about turning off things and turning off money. Eventually it becomes too expensive to operate it. If you're not getting much data back and you're paying some team $10 million a year to operate, that becomes uneconomical. Or there will be some kind of failure of the spacecraft. This thing, when we're at Perihelia, we have to keep it pointed at the sun. Okay, so there's a closed loop system. There are star sensors that see measure an inertial coordinate system by looking at the stars and recognizing the stars. There are limb sensors that sense the limb of the spacecraft, that know where the sun is. There are gyroscopes, so basically what we call reaction wheels, momentum wheels that keep the thing pointed. They have to be unloaded, so they build up enough momentum and then you have to use hydrazine gas to unload them. So if we run out of hydrazine gas, if the reaction wheels, the momentum wheels start to fail, if the limb sensors, the star cameras fail, the spacecraft won't stay pointed at Perihelia and then it'll just burn up. But if it's all working, we always try to make a case to NASA to keep funding us and keep taking data. And some missions, the WIND mission was launched in 1994. It was supposed to be a 2-year-long mission, and we're still operating it today.
Yeah, this is a theoretical question. I'm just curious, how would these models and data apply to a star of a different size? Like say a larger one than ours would be similar, different?
That's a good question. I'm not an expert on all kinds of winds. There's a whole class of stellar winds. Our wind is thought to be an alphanic wave-driven wind, but there are winds that are driven by thermal gradients, or winds that are driven by dust, etc. Hopefully what we learn from Solar Probe will at least apply to alpine wave-driven kind of winds. It's interesting, actually, I brought this up in one of the first slides too, that this Parker Solar Wind model is essentially identical to the simple model of bodies accretion model, which has critical points, zero angular momentum, etc. And there are people I know, maybe in this room, who believe that the interface between a black hole and its accretion disk is in some ways similar to a wind acceleration region. So there may be broader ways to interpret the data in terms of other plasma astrophysics problems too.
So what determines the shape of the source surface? Do you have any models for that?
The standard model up until today is a sphere. Okay, so just because it's because you can solve you can spherical harmonics to solve the problem. Okay, so there's a spherical source surface, and that height has canonically been taken as 2.5 solar radii, which comes from two things. It comes from looking at images of the sun and seeing kind of the typical height of loops. So you want to have, you want to have the open field at that surface, and you don't want to have closed field at that surface. And it also comes from considerations of the total amount of magnetic flux in the heliosphere. So if you make measurements using other spacecraft, just measure the magnetic flux at different points. That's related to how low, the lower you put that source surface, the more flux you're opening. So those are the two constraints, and the canonical value is 2.5 solar radii. What we're finding is that we need often to go much lower, and that's already kind of getting to be controversial. We've got referees reports from the first papers, and people are wondering about that. But it's very no, it wasn't very consistent. But it's very consistent with the data. There's no way to reproduce the data with the 2.5 solar source surface. But the structure of it, I think, is just the the longitudinal structure is just related to magnetic pressure, probably below. It's if there's a lot of magnetic pressure below the source surface height, might be higher, etc. So it's probably related to the pressure in the loops below the source.
At the spacecraft's current position, only the tips of the solar panels are raised.
That's right.
They use the coolant, but still, what is the temperature?
Of the solar panels themselves?
The tips that are exposed.
Boy, I don't know exactly, but I would guess that most of the temperatures we quote are for the model predictions for the lowest perihelia, 9.86, which is what we designed to. So the front surface is meant to go to 2200 C, which is a big cross-section. My little antennas, which are metal, which are niobium alloy, and they're very shiny, will float at about 1300 C. So I would guess somewhere probably closer to that. The solar panels themselves have a kind of shiny glass surface. They're dark below, probably 13 to 1500 C or so. But they're cooled too. They're actively cooled, so that'll pull heat off the back of them.
You mentioned lots of other instruments that measure the presence of charged particles
Yes.
in the plasma. What sort of? I mean, they look like curious instruments. They look like sort of hedgehogs with their spines cut off or something. How do colanders? How do those things actually work?
Yeah, I mean the one. So these are the guys. These are the ones who measure the energetic particles, right? So this thing, right? We've been calling either the mushroom or the porcupine in a kind of pejorative sense. His team doesn't call it that, but we call it that. They basically have a bunch of apertures that look in different directions, and they have some tolerance. They let the particles through, and they have solid state detectors behind them, and they try to create a map, in the sky of the particle fluxes. These instruments tend to be pretty simple. There's another one. This is actually called epi-low. There's another instrument somewhere around here called epi-high, which is even simpler. It doesn't have as much directionality to it. It just has some open apertures that look in the sky. So they haven't seen very much yet, and the reason they haven't seen very much, they've seen a few events associated with shocks low in the corona, what are called coronal mass ejections, these big magnetic loops driving outward. And they've seen particles accelerated below the spacecraft and below the corona propagating out. But I think the reason they haven't seen very much is because we're at solar minimum right now. So the sun is pretty quiet. So there's not a lot of impulsive activity, which is also why our really simple magnetic field model works. Once we start to get, what are called active regions, flaring regions on the surface of the sun, that simple magnetic field model can work as well there. Did I answer the question?
Yeah. I was just thinking, if you've got 100 MeV proton hitting one of these sensors on the inside, that leaves a bit of a mess inside.
It's designed for that. I mean, the fluences are small. Okay, so actually the energetic particle, that's a good question. The energetic particle environment here, from penetrating ionization is not all that bad. There was a mission done about I guess 2012 or something, launched in the US called the Van Allen probes that went into the radiation belts of the Earth. Much more nasty radiation environment than this thing. In particular, our radiation requirement here is 100 kilorads behind a millimeter of aluminum, so it's not too
What do you think causes the surface to be so significantly non-spherical?
The magnetic field. The structure.
The source surface.
Sorry?
The source surface.
Oh, the source surface, the non-radial source surface. I think this is just due to the fact that the field below, so it's a balance between the wind, you know, the energy density in these closed loops can be higher than the energy density in open field lines. Okay, so I think that's probably part of the story, is that where you have more loop-like structure, that there's more energy to hold the plasma down than when there's open field. So it has something to do with what opens the field, okay, which is probably magnetic reconnections at these current sheet boundaries. So it's not a surprise in a sense, as long as there's inhomogeneous structure in the loops. I think the surface height, which is just a balance between the energy densities, is going to be inhomogeneous as well. But what's really cool, I think, is that we can sort of measure it. We can sort of measure that, and eventually we'll be able to compare it with, we haven't got there yet, but we'll be able to compare it with these kind of images of loops and see if that picture hangs together. And it also is going to tell us something about the wind speed at these low heights, because at some point, and this is and notionally that circle is where the energy density in the plasma is equal to the energy density in the field plus gravity. So it tells us something about the energy density in the plasma at that height, which is related to the speed, thermal energy. It's crude, but it works shockingly well for these simple first few perihelia where we don't have any active regions on the sun, where we just have simple magnetic field. Solar minimum.
So do you reckon you make a few trips to hell and back, as it were, reconstruct at each of these trips, reconstruct that surface, then average over all these different surfaces you've reconstructed? Do you reckon you're going to get a sphere?
I wonder. I mean, I haven't. What I think to do is actually to reconstruct the surface like this, and then compare it to some other, fiducial of the energy density below it, loops, for example, and try to do that over time and see if there's some simple correspondence.
Is what we're looking at basically a sort of a sphere plus delta sphere?
Yeah, I think it is. I think it probably is. Yes, I think it's probably sphere plus delta sphere.
Any more hands up? Oh yes,
That.
please.
Are there concepts to use the solar wind to sail into the light sail?
Sorry, I didn't understand this.
Are there concepts to use the solar wind as a could you sail in the solar wind?
For solar sailing?
Yeah.
I mean, yes, there are concepts to do this, yeah. And there have been sort of test flights of things to try to do solar sailing and tacking and that sort of thing. I don't think it's been used yet on, at 1AU and beyond 1AU, actually from, the Alpine point, but let's say Mercury, at least from Mercury outward, the wind speed is fairly steady. Okay, it asymptotes up to this speed. Okay, it's bimodal, there's fast wind and slow wind, but it's fairly steady outward, all the way probably to the heliopause, to the edge of the solar system. So going from 1AU out might not be too hard. I don't know. But there are people who work on the solar sailing stuff.
Right. Well, it appears that we have momentarily exhausted your appetite for questions. So let's thank the speaker now, and then we'll move on.